In this problem, this lecture, we look at some basic algebra rules about derivatives. Suppose we have two functions, f1 and f2, and we know how to take their derivatives. What's the derivative of their sum? By the definition of the derivative of the sum would be this. We'd take the limit as h goes to 0 of f1 of x plus h plus f2 of x plus h, and we subtract off f1 of x plus f2 of x. So on top is the change in y, and then on the bottom is the change in x, or h. Now we can rewrite the numerator and use some simple algebra to get the following. I'm going to pull different pieces together. I pull f1x over here, so I have f1 x plus h minus f1. And then on the right side, I've just rearranged the numerator to get this expression. So I've not changed things at all. But by our limit laws, the first one is going to be the limit, it's going to be the derivative of f1, and the second piece is the derivative of f2, so we get f1 prime plus f2 prime. In other words, the derivative of the sum of functions is the sum of the derivatives. We've just argued this from the definition of the derivative, but it's a rather natural idea. The derivative of a sum is the sum of the derivatives. This is natural and easy to use. There's no reason to memorize it. For example, if you're given this function, f of x is x cubed plus x squared plus sine x, then the derivative is just 3x squared plus 2x plus cosine. A similar result occurs if we multiply our function by a real number. This multiplication is often called multiplying by a scalar, since it has the effect of rescaling our function. So multiplying by a constant is said to be scalar multiplication. It's very different between multiplying by a constant and multiplying by some other function. Here we're just going to multiply by some constant. For example, we know the derivative of sine x. What do you think is the derivative of 5 sine x? We would hope that if the derivative of sine x is cosine x, then the derivative of 5 sine x is 5 cosine x. And yes, this is right. I can argue this by the definition of the derivative. Here I have a function that is a scalar c times f of x, and I write out the derivative using the definition. Notice that since g is c times f of x, I can rewrite g in terms of this scalar c, and I can factor c out of the numerator, pulling it all the way out so that I'm taking this limit. And what is that? This is just c, the scalar, times this limit, and you should recognize this as, by the definition, the derivative of f. So my answer is c times the derivative of f. The derivative of a scalar times my function, it's just a scalar times f prime. Again, this is a very natural rule. The derivative of a scalar multiple of a function is the scalar multiple of the derivative. For example, suppose we know the derivatives of x cubed and x squared and sine x from the last lecture. Then what would be the derivative of 5x cubed plus 13x squared minus 100 sine x? Well, it's simply going to be this. The derivative of x cubed is 3x squared, so the derivative of 5x cubed is 15x squared. The derivative of 13x squared is 26x. The derivative of 100 sine x is 100 cosine x, and then we add them up. Let's find the derivative of the following functions. Suppose I have any of these three functions. We'll work through these. The first function I can rewrite using properties of exponents. 5 over x is the same as 5x to the minus 1, and 3 square root of x is the same as 3x to the 1/2. Using the power rule and adding things up, I get this answer. So the derivative of x to the minus 1 is minus 1x to the minus 2. So the derivative of 5x to the minus 1, 5x to the minus 1 is 5 minus 5x to the minus 2, and so on. The second problem, I can rewrite using the power rule as 10x to the minus 3 halves. That square root of x cubed in the denominator is x to the minus 3 halves. And then all the rest of these, 17e, pi, and this thing, are all constants. And what's the derivative of a constant? It's 0. So my derivative is minus 15x to the minus 5 halves plus 0, or minus 15 over x to the 5 halves. If g of t is this expression, I can square this out and expand it to rewrite the problem this way, and then power rules and derivatives of constants being 0, derivative of e to the t is e to the t, so there's my answer. If I have these simple algebra rules, then I can extend my derivative rules to a wide range of functions. These results are natural and straightforward. I never memorize that the sum of derivatives is the derivative of the sum, and vice versa. But the product of two functions is more complicated, and the derivative of a quotient is even worse. We do need to work on those two properties, and that will be the subject of the next lecture.